Hello, everybody. And I should say that I'm very grateful for the organizers for this kind invitation to have a talk on the workshop, and it's a big honor for me. Today I will talk about some common work with Josef Strejčka, and it will relate to this Shastry-Sutherland model, the model which was already mentioned and reviewed by Andreas Honecker on the first day on Monday. He was concentrated mainly on thermodynamic properties, and our focus is a bit different. We consider ground state properties and looking for some peculiar possible quantum states in such a model. And so the outline of my talk is as follows. I will start with the introduction, then I will I will talk about Ising-Heisenberg model as an example, as a good starting point for developing perturbation theory. And then we consider two different limits in Shastry-Sutherland model, like low field limit and high field limit, and see what interesting quantum phases can appear over there. I will just briefly remind you about Shastry-Sutherland model. It was suggested in 1981 by Shastry and Sutherland, like a model of mutually orthogonal dimers, and just the interest was purely academic. Like this model has exact ground states of singlet dimers, and in fact, the state depends on the ratio between intradimer J and interdimer J prime couplings, and can be changed from singlet dimmer to placket and further to Niel ground state. But what arises interest to this model is that Kagayama revealed that Stronci-Cooper borate is an exact, nearly exact realization of this model, and they measured magnetization and found 1/8 and 1/4 plateau, and people started looking at this model and do other experiments, and then more magnetization plateau was revealed. Now it is like firmly established that there is 1/8, 2/15, 1/6, and 1/4, and 1/3 and 1/2 plateau. And needless to say that it's very hard to do theoretical research in this model, because it is frustrated, it is two-dimensional, and analytical methods are quite poor. And if you're looking at the perturbation expansion about non-interacting dimers, it is very weakly convergent. So for instance, fourth order perturbation expansion reveals just 1/4 plateau. Also, one can apply some more exotic method like two-dimensional Jordan-Wigner transformation, but this method contains some non-controlled assumption. Numerics is also quite hard, as I mentioned, because it's frustrated. So Monte Carlo usually was not possible to apply here, except for the last years when this quantum Monte Carlo on dimmer basis was invented, as it was reviewed by Andreas. Other methods like exact diagonalization and DMRG method are suffered from finite size, and it is quite hard to extend this result to infinity. I will touch this question later. But usually, since the model is consistent with orthogonal dimers, as was mentioned by Andreas, it is an example of flat band physics. So dimmer excitations, which is called triplons. Triplons is excitation on dimmer from singlet to polarized triplet state, are usually localized because of this configuration of orthogonal dimers. But nevertheless, there exists may exist some quantum phase, and here is a result of experiment published in 2005, and people measured and then calculated the excitation gap between in strands equiborate. So when so the excitation gap is in principle kind of localized excitation of singlets on dimer to triplet, and it is quite clear that when we apply external field, it should decreases linearly with the field due to this Zeeman coupling with field. And but then what is interesting, it goes down, but very close to the point when one can observe 1/8 plateau. This curve deviates from linear rule, and that's probably some sign of some new quantum phase, which is still not so good learned. And as I will tell you, probably it's like it is constituted by the bound triplon phases, which is quantum, in fact. Okay, so let's go to the method. Some parts of it was already mentioned by Joseph last year on this workshop, but I just repeat it for the completeness. So what is important in perturbation theory? It's important to choose some zero Hamiltonians so we can so this perturbation theory will be convergent. And sometimes this choice is not so evident, but in our case, we will choose this model like some kind of caricature of Shastry-Sutherland model, which we called Ising-Heisenberg, where interdimer couplings are replaced from interdimer couplings, the quantum part of XY interaction is removed. So we have Heisenberg coupling between spin inside dimer and Ising outside dimer. And this is maybe not so big simplification, but it is crucial because then model gains a lot of conservative quantities. For instance, total Z component on a dimer is conserved quantities. Also, we can consider our Hamiltonian as a sum of such kind of cluster Hamiltonian of coupled 3 consecutive dimers. And these Hamiltonians also commute with each other. That means that their energies are conservative and they can be diagonalized independent with each other. And in fact, what that means that we can diagonalize each cluster, and in what finally we get kind of classical representation of the model. And this is this kind of transformation which leads to the classical representation. Maybe in the future we will consider 2 pictures. One is just picture when instead of spins on a dimer, we will look just on a dimers states like it's written over here. Because when we are talking about dimer states, we are talking about singlet, which we call 0 state, and then 1, 2, 3 states, which are spin Z1, 0, -1 triplets. And since it's classical model, so we just need to find the right configuration on dimer states and prove that it is has the lowest eigenstate. And it's in principle, in this case, it is not so difficult. So we found it, and the ground state phase diagram looks like that. For small field and strong intradimer couplings, we have singlet dimer phase, which means like the same state which got Shastry and Sutherland. singles dimers on single states on each dimer. And if we increase inter-dimer coupling J prime, the ground state immediately turns to antiferromagnetic state. That actually shows that our model is not so good in this limit, because if you compare with Heisenberg model, Plackett phase is missed in this phase diagram. Therefore, when we would like to perform perturbation theory, starting from using Heisenberg model, we should be confined by the point when J prime is less than 0.7, actually more or less this limit point when in Heisenberg model singlet dimer states is still the ground state. When we increase the field, the next phase is stripe, 1/3 plateau phase, which can be also proven quite easily. Like when we look at this our Hamiltonian as a sum of this cluster dimers. So 1/3 plateau phase is a phase which is composed on such a cluster when just one cluster inside one dimer inside cluster is excited to triplum state. It can be anywhere, either in the middle or at the edge of this cluster. And if you try to solve this geometrical problem, what kind of phase you can build from such a three configurations, it is just 1/3 plateau phase. And finally, for higher field, we got checkerboard 1/2 plateau phase, which means that either horizontal dimers are polarized or vertical dimers are polarized. Still, it can be, this phase can be built from the state of clusters when three types of cluster, when either middle spins are excited or pair of H spins are excited in triplet state. In principle, we can so the ground state, this edge, this transition fields in the ground state phase diagram can be also calculated rather straightforwardly, and we got the simple results. Unfortunately, we have exact results relates only to the ground state. If you're looking, if you would like to look at the temperature effects, it is not exactly solvable anymore, since interaction between spins inside this cluster are quite complicated. What is still interesting in the ground state at the transition field between different phases, and it is macroscopically degenerate for some specific case, like for the transition between the singlet dimer and 1/3 plateau phase, as well as for the transition between checkerboard and saturated phase. For instance, if you look at the transition between singlet dimer and stripe phase, 1/3 plateau stripe phase, we can see that we may have dimer cluster dimers or dimer clusters of 3 or 4 possible configuration. Either all are in singlets or one of them are in triplet. And that means that if you excite, say, triplon in this particular dimer, then no other triplons can be excited in this red dimers, because it will break the rule which I mentioned right now. Then that means that, for instance, okay, sorry, if you consider opposite case of high fields, in that case it is transition field between this 1/2 plateau phase, checkerboard one, when just half of dimers are excited, and completely polarized phase. And elementary excitation at the transition point is, in that case, it's not triplon, but we call it magnon, because it's excitation of dimer from ordered triplet state to singlet state. And this magnon also should fulfill hardcore condition, because of this set of possible cluster configuration in between on the transition field. Just to mention, we have two kind of excitation. If you have low field, we have triplon excitation among the sea of singlets, and in case of high field, we have magnon excitation still with hardcore condition, although in some different way in the sea of polarized triplet state. And this is quite good starting point for the many-body perturbation theory. Here I just mentioned this schematically general equations for many-body perturbation theory. And it is quite similar to what we know from normal quantum mechanics for non-many-body theory. So we have decomposed Hamiltonian in zero part and ideal part zero, for which we know all the eigenstates and eigenenergies and perturbations. Call it H1, and we introduce P as a projection to the known ground state phi0. And finally, we can build from this some series of series expansion and find effective Hamiltonian in a series on lambda. Usually, we confined by second order perturbation theory, because higher perturbation terms are quite intricate. So what we did was consider finally to come back. If you are looking at the low field case, we consider the effective Hamiltonian as a perturbation from Ising-Heisenberg. Effective Hamiltonian can be found in the perturbation theory when we suppose zero Hamiltonian is Ising-Heisenberg Hamiltonian, and the rest, which means xy part of the interdimer coupling and deviation from critical field is a perturbation. And effective Hamiltonian in this case is a Hamiltonian in terms of triplons, and NL is operators occupation number of triplons on the dimer side. And it contains several terms, unary term like energy of isolated triplon, then couplings, pair couplings, like coupling between triplons on the nearest possible position and further neighbors. There are three types of these couplings. There are also many types of three-particle coupling, which are much less. And also there are many body coupling like 4 and 5-particle couplings, but we omit this because actually they are in order much less than other terms. And except that, there is also some special term. There is no, in this effective model, that it is known even before that effective model for this triple excitation lacks the direct quantum terms because of this special orientation of orthogonal dimers. But nevertheless, there is a terms which are called correlated coupling or correlated tunneling or assisted tunneling term. So we see that this tunneling from site I-1 to I+1 is possible only in case on the diagonal we have dimmer in triplet in triplon state. It is visualized here. So pair of triplons can be mobile only in case they are nearest neighbors on a diagonal. Otherwise, they are localized. And later we show that this term is can be quite important at low field. And if you look at effective couplings, how they depend on the interdimmer coupling J prime, you see that the most strongest contribution has this pair interaction between nearest dimmers W1, V1, but even at small J prime, this correlated tunneling is competing with this term also, and then we will see that it is important. There's then couplings between further neighbor couplings are much smaller than nearest neighbor one, and if you look at the three particle couplings, they are almost an order less than pair coupling. So they do not actually change the phase diagram a lot quantitatively, but qualitatively they are important because some phases can be still degenerate, and it, for instance, is responsible for a stripe-like phase of 1/4 plateau phase. Finally, we could found this phase diagram. It's quite hard still. This problem is quite hard, but if you omit correlated tunneling term, we can find the phase diagram in terms of classical localized triplons, and all these phases are still the eigenstates of our effective Hamiltonian. Since, for instance, if you look at the 1/8 plateau, which is highly degenerate, it contains well-separated triplons, which surely can, and if we apply the quantum terms to it, the matrix element, corresponding matrix element are 0. And so finally, we got in this model additional 1/8, 1/6 plateau like here, 1/4 stripe-like plateau like here, and 1/3 plateau was actually is in the Heisenberg model already. That means that using the second order perturbation theory, we obtained the most important plateau which were observed in strontium copper borate. And if you compare our results with the available numerical results from Corey method or IPEPS method, we see that it is very, very precise up till 0.5 and still up to 10% precision for 0.6, which is kind of limit of existing of spin single dimmer phase in this model. But why this correlated tunneling term might be important and how we can treat it? Imagine we do not neglect this, and we still preserve it in the Hamiltonian, and then if we would like to visualize our possible quantum state, we can see that our triplons should be connected into bound state. In that case, then they can tunnel, but their transport is also effectively one-dimensional. So horizontal triplons can jump in horizontal direction, vertical in vertical directions, and in fact there can be thermodynamically large number of such kind of excitation, and quite hard to find to treat this model because we have several very hard interaction, like say assistant tunneling or correlated tunneling itself. It's quite hard to treat, but we also have very extended hardcore conditions. So this shadowed region means that region where these triplons cannot be put on it. But if we are looking for the ground state or for the lowest eigenstate of such a model, we can devise, for instance, that maybe that's energetically most favorable for such a system that these bound triplons are creating something like stripe phase when they are arranged along one pair of line, and two other lines are free of triplons. Otherwise, if we have some disordered mixture, this bound triplon states should fill each other through this hardcore condition. It may cost a lot of energy. Of course, it's like quite hand-waving argument, but nevertheless, I will show you later that such kind of phase has been found in using the MRG method for so-called Shastry-Sutherland tube. And we will see even which kind of width of the Shastry-Sutherland tube should be in order to get this to get the correct results for the two-dimensional Shastry-Sutherland model. And of course, we cannot find the complete quantum state, but we can find the energy of some separate triplon bounds, and if this energy is becoming less than energy of two excited triplon, then it will say that this bound triplon state may emerge in our state, in our model. And so this kind, then we can consider kind of caricature on this two-dimensional model, like just one stripe of bound triplons. And if we denote instead of bound triplon some effective boson, hardcore boson particle, we can write the effective Hamiltonian of bound of these effective bosons, which each boson creates a pair of triplons. And then find the one particle excitation, energy of this one particle excitation, and compare this with the energy of two delocalized triplons. And we see that always the energy of these bound triplons is less than energy of two delocalized triplons. Therefore, we know that that this that is bound triplon quantum phase appear just the first one when we apply field. Of course, we don't know what happened after that. How when we have the transition between bound triplon and 1/8 plateau phase, whether we have it in fact. But we know that, for instance, this energy of bound triplon phase is for sure much larger than energy of 1/4 plateau phase. So usually we can suspect that it is quite small. This stripe, when 1/8 this bound triplon state is leaving. And as I mentioned, it's quite hard to find to do numerics for this model, and usually when doing numerics, we can do we should confine ourselves by finite systems, by some different geometries. And one example, the simplest, is orthogonal Dimmer chain, but it is more academic, and it is like doesn't have so much correspondence to Shastry-Sutherland model. But if you consider two coupled chains, is periodic boundary condition between this edge spins, which is like pink one. It called it two-leg Shastry-Sutherland tube. If you increase number of tubes to 4, it's 4-leg tube, and of course, if it's infinite leg tube, it's like normal Shastry-Sutherland model with periodic boundary conditions. But this kind of tubes are 2 and 4-leg tube are in principle are quite good for DMRG calculation, and such a calculation has been done. But before, I would like to mention about the ground state of Ising-Heisenberg model on this geometries. So, for instance, Ising-Heisenberg model or orthogonal Dimmer chain have quite similar number of phases to Ising-Heisenberg Shastry-Sutherland model. Okay, not really, but it has 0 Plato singlet Dimmer phase, like it's written here. Then modulated ferromagnetic phase, which like staggering one vertical Dimmer up, and then next in singlet phase and so on. Then 1/2 Plateau staggered bond phase, like that one, and saturated phase. If we consider Shastry-Sutherland tube, which consists of 2 orthogonal Dimmer chain connected and periodically coupled along vertical direction, we still have the similar phases, but phase diagram is a bit different. So we have singlet Dimmer phase, like singlet Dimmers between these 2 coupled chains, and we have 1/4 Plateau phase, which is reminiscent of orthogonal Dimmer chain, just like each chain has its own 1/4 Plateau phase. And we have staggered bond phase, and we have also like phase, but we don't have 1/3 Plateau phase over here, for instance. And if you look on 4-leg Shastry-Sutherland tube, we can see the phase diagram is completely the same, and phases are also completely the same. Like we should add two more chains to this picture, and we get 1/4 Plateau stripe-like phase and staggered bond phase. And interesting to understand why it is not possible to get 1/3 Plateau phase, which is still in 2-dimensional Shastry-Sutherland model. And this 1/3 Plateau phase in Shastry-Sutherland model is built from looks like the stripe-like, when stripe of horizontal Dimmers are alternating by stripe of vertical Dimmers, and between these Dimmers are 2 stripes of singlet states. And just to remind, the condition is that each cluster Hamiltonian should contain just one triplet state. But in case of this geometry or 4 tube, this kind of triplet state, which seems to be well separated, are not in fact separated, because we have periodic boundary condition between connecting these 2 spins, and therefore such state is not a ground state, and no 1/3 Plateau state can be found in 4-leg Shastry-Sutherland model. But if you look at the, say, 6-leg and more leg Shastry-Sutherland tube, this restriction is not valid anymore, and we got the same phase diagram and in Shastry-Sutherland model. Then if you look at this, that was case of exact Ising-Heisenberg model, when we can do everything rigorously. But what happens if we have Heisenberg model on our model with restricted geometry? It is known that in orthogonal Dimmer chain we have a series of magnetization plateau between 1/4 and 1/2 plateau. And if you consider 2-leg tube, what we have new? We have new additional 1/6 plateau, and still seems to be the same series of plateau between 1/2 and 1/4 and 1/2 plateau, and additional 3/4 plateau between 1/2 and saturated magnetization. But unfortunately, no quantum phase. That was a result of the MRG calculation in one of his co-authors in 2011.
Professor Torres?
Yeah. So is everything fine, or can you hear me or see? So may I continue?
I think that they lost the connection.
Wow. So you don't see
We are
me?
alone. We are alone here. What's recording, né? Deixa eu perguntar. I will ask some of them. Bye.
So there is no connection, or what? Or already it is recovered?
Okay.
Okay, maybe I try to do something different. A window, and then like that. So how about now? Is it okay, or can I continue or not? Or still there is no connection? No.
I think it's okay. I think that the organizer was the.
So there is no.
There is no connection for them, but.
We can continue. You think we can continue? I can continue just without organizers, yeah?
Yes.
Uh-huh.
I think that you can wait until the.
Okay. Thanks for that.
No, don't worry.
Okay, so I don't know. Azadeh told me that online you can see me, but organizers has lost connection. So I don't know what is how we can proceed if we are if we can wait for them, or there is no anybody connecting to the organizers to tell me.
I'm talking with them here.
So let's wait, or
For those for Google Group, I hear you. Looks like it's stabilized right now. We can
So we have connection right now, yeah. So I can continue.
continue, please.
Yeah. Okay. Thank you very much. So the MRG, if you increase number or legs in Shastry-Sutherland tube, the calculation becomes quite hard and time consuming and resource consuming. Therefore, there is no phase diagram, but just Faltin, Mana, and Kai Schmidt did this calculation for some particular J prime over J, and for quite a limited number of dimers, like 4 times 8 and 4 times 16, for 0.3 ratio between interdimer and intradimer coupling, and 0.6 or 67 over here. And what they found, 1/8 plateau everywhere and 1/4 plateau, no 1/6 plateau, but that's probably quite clear because the size of their system is not divisible by 3 or by 6. So quite hard to expect to get this plateau in this case. And we can see even that near zero magnetization, this curve, it's hard to see, but still there are a lot of, there are several steps, so it probably the sign of this quantum phase. But even more, when they looked at the magnetization of 1/8 plateau, magnetization profile, they found this kind of stripe-like phase. You can see that dimers are here drawn like has these sides which more these red dots, red circles means larger magnetizations, and we see stripe-like phase either in direction perpendicular to tube, or also the same phase can be found was found in longitudinal along the tube, which actually probably means that such a phase can appear in two-dimensional Shastry-Sutherland model. And if you compare this point of critical field, it completely coincides for 0.3, and for 0.6 we have deviation 10% from our results from numerical DMRG, which are exact in this case. Sorry, maybe I forgot. And finally, I would like to talk about high field system. Usually, all the study is done either at lower field, or quite new results concern the pressure, when you can change the interaction ratio and lead the system to this Blackett phase and even to Niel phase. But since to polarize, to go beyond 1/2 plateau, physically in strontium copper borate, it is need magnetic field more than 100 Tesla. It is even not realizable right now, I guess, to reach the saturation, and therefore interest to this part is not so big, and there is not so many studies, and but still we would like to consider it and to see what the physics for high field regime. And if you start from our case from this zero Hamiltonian, which is in Heisenberg one, we should consider perturbation about the transition field from 1/2 checkerboard plateau and saturation, and elementary excitation in that case are magnons of on dimers from this polarized triplet to singlet state, and it has it should fulfill this hardcore condition, which is written over here. And therefore, this effective field, we obtain effective field, and it contains several terms per interaction, like interaction between nearest neighbor of triplets in one direction, vertical and horizontal one, and also interaction between three magnons and even 4 magnons. But what is interesting that it also contains now the direct quantum terms, which describes transition of magnons along their orientation. But also, in addition, it contains assisted tunneling, but even by two magnons. And Unfortunately, I didn't give here the numbers of such a coupling, but surprisingly, the square coupling and three-particle coupling are the largest one, and they compete with each other. And all other couplings are of the same order, like this tunneling and pair coupling. And in general, it is quite hard to analyze this model, even effective one. It would be interesting to find some solutions. But what we can do, we can still find the critical field using our effective model, because it's quite simple. We have to find the condition for zero excitation for these two limits of saturated and one-half plateau phase. And here we compare our results with the numerical results, and we see that these symbols are IPEP's result, and result by IPEP's method, and this blue dashed line are results of our effective model, which is still rather good till 0.6. And dashed this violet model corresponds to our to the saturated phase within our effective model, and we see that the agreement with the exact saturation field is not so good, in fact. But that's because of the scale. If you look at the scale, normal scale, we see that it's still within 10%. And just for your curiosity, this short dashed red line corresponds to the transition field between one-half plateau and saturation of Ising-Heisenberg model. But still, the microscopic study of this model could be interesting, and probably, like in Heisenberg tube, here we can find some intermediate 3/4 plateau for the Shastry-Sutherland model. So I will conclude and say that we considered some different dependence on the sizes of Shastry-Sutherland model, considering Shastry-Sutherland tubes, and showed that the size of this tube should be at least 6 leg, should contain at least 6 leg. So we also analyzed quantum phase of bound triplons and find the correspondence to this to the phases obtained in DMRG for 4 leg Shastry-Sutherland tube. And the effective model for the description of Shastry-Sutherland model at high fields contains magnonic excitation, which are both delocalized and okay, it's still quite difficult to study, but the whole interplay of all these terms may lead to some very interesting quantum phases, even at high fields of this model. That is all. Thank you for your attention.
Thank you, Professor Taras. Thank you, Taras. Yeah, sorry for the instability of the internet here, but now looks like we come back. Okay, questions here on the chat? Please, if anyone has some question in the chat, raise your hand, please. I think no one here. No one in the chat. Okay, I have one question.
Okay.
About your perturbative approach, you can apply this only from the mixed model using Heisenberg model, or for the full Heisenberg chain, Shastry-Sutherland chain, we can apply the same idea. Thank you.
Sorry, because I couldn't hear quite well. Can you repeat it?
I was asking if the perturbative approach that you're using in this model,
Yeah.
You using only from the Ising-Heisenberg mixed chain, or you can apply for the full Heisenberg chain from that model, Shastry-Sutherland model.
Okay, actually that was like a perturbation. We use using Heisenberg as a starting point for our perturbation theory. So our interest is Heisenberg model, but then we divided it into parts, using Heisenberg and the rest of the model. And this perturbation relates actually to this perturbation. So yes, we can consider Heisenberg model. Actually, that's what we did.
Okay, thank you. Any more question? Okay, so let's thank our speaker again.
Yeah.
Oh, sorry. There's one question here in the chat. You can see the question? I can hear for you.
Yeah, we consider another system where this model is applied. You mean physical system? Yeah, there are several systems. Maybe the most known among them is tetraborates, although that's kind of different because it is either Ising model, completely Ising model, but which contains also strong, but the material is also a metal. Therefore, there is a strong correlation between conductivity electrons and Ising moments. And also there are another model, I don't remember exactly which one, the name, not my model material, but it concerns the ferromagnetic inter-dimer coupling. Therefore, it is not so interesting because it doesn't have any this rich structure of fractional plateaus.
Okay, last question. Any question? Okay, now we can think. Taras finally. Yeah, next talk is some few minutes. It will be Marcelo Lira, and we'll be back in 20 minutes. Okay, thank you.